Good afternoon, everyone, and thanks for joining us.
Good afternoon.
Good afternoon. We will be commencing in 2 minutes. Let's wait for 2 p.m. Jamaica time sharp to start. We already have quite a good attendance so far, 42 people, which is quite good. And then we can start directly with the introduction of our team, of the project, and the rest of the training. Okay, I think we can start. Welcome everyone. I am Simone Landucci. I am an urban planner and GIS specialist at OpenPlan, a consultancy firm based in the UK. And I'm here joined by my colleagues in this project, which are Steve Kemp, Jonathan McHugh, Yolanda Aline, and Theodore Allen, which have turned, if they could please turn the camera on, will be shortly joined by other members of our team. But in the meantime, we'll start with an introduction from Mr. Kemp. We want to start by thanking the UE Mona for organizing this training and for managing the Zoom invitation and the invitation process. Just a few housekeeping consideration. So please keep your microphone muted while you're not talking or we are not asking a question. To ask question, it would be best if you could use the chat or raise your hand, and in the Q&A sessions, which will be at different steps during the training, we will collect some questions and answer them. There's quite a few of us today. We are 53 and rising, which means that it will be much easier and smoother to manage the Q&A using the chat itself. The practical part, which is the second part of today and basically the whole of tomorrow, because this is a 3 days training, it's a practical exercise which you can follow online using the software that you should have downloaded. There was some links to download and install the software on the invitation email, and you can use the data set that it was provided to you. So hopefully you will be able to follow through the presentation, follow through what I and my colleagues will be doing on the softwares. And if there is any problems, you can raise questions, and we will collect some of those questions, some of those key issues arising, and we'll address them. That being said, I think we could have a round of presentations, starting with Steve, of the members of the team here today. So Steve, if you could introduce yourself briefly.
Yes, thank you, Simone. Yes, I'm Steve Kemp. I'm a spatial planner and placemaking enthusiast, I would say, and I'm also from OpenPlan.
Okay, maybe we can have John, if you could introduce yourself as well.
Yes, hi, good afternoon, everybody. Jonathan McHugh from Sustainable Seas. I'm brought in as the ICZN specialist to support the OpenPlan team and to provide some direction to support the INVEST software.
Thank you, John. Yolanda.
Hi, good afternoon, everyone. I'm Yolanda Aline. I'm an urban planner and an environmental planner, and I'm based in Barbados, and I am here to give support to Steve as co-lead on the project.
Okay, thank you. Teddy.
Good afternoon, everyone. My name is Teddy Allen. I'm a climate scientist with a background in marine meteorology and climatology. I'm here to support the project in terms of the data information and the data ingestion into the model. And I'm based here in Barbados as well.
Okay. Then we have Miguel, if you could introduce yourself as well. Okay, we might have some technical problem here. In that case, we will present to the rest of the team later on during Steve's presentation, but now I'll leave the floor to Dr. Stevenson from UWI Mona for the UWI welcoming and introduction. Please, Dr. Stevenson.
Thank you so much, Simone. Can you confirm that you're hearing me well, please?
Yeah, we are. At least I am.
Thank you. Thank you so much. Mr. Gerard Allen, climate change specialist in the Inter-American Development Bank. Dr. Georgiana Gordon-Strong, project director of the pilot program for climate resilience and the project management unit, including Ms. Erica Horton, project manager. Prof. Michael Taylor, Dean of the Faculty of Science and Technology and co-director of the Climate Studies Group, Mona, at the University of the West Indies. Distinguished ladies and gentlemen, welcome. On behalf of the University of the West Indies Mona campus in Jamaica and under the auspices of the pilot program for climate resilience funded by the Inter-American Development Bank under the Climate Investment Funds, welcome to this training workshop in coastal scenarios for land use and planning. I'm Tanisha Stevenson, co-director of the Climate Studies Group Mona at the University of the West Indies. Please allow me to also acknowledge Mrs. Marcia Curry-Ford from the U.S. Center for Marine Sciences and Ms. Monique Curtis from the National Environmental Planning Agency in Jamaica, who are members of the Technical Advisory Committee under the component that this activity is being hosted under. We also acknowledge the training team, OpenPlan and OIKO. This training, our colleagues, is a part of activities that are being facilitated under component 3, downscaling and expanding climate projection models and high resolution maps under the PPCR. And the focus, ladies and gentlemen, is that development of land use or planning coastal scenarios for select sites across the pilot countries under the PPCR. These scenarios that will be presented today are meant to be case studies to guide future work. You'll hear of other deliverables under the activity, including a framework that has been developed and will be shared with our region that will enable us to develop other coastal scenarios. Importantly, our colleagues, the anticipation of this effort is that we'll build human resource capacity within our region through the provision of this kind of training. And so we'll be better placed to utilize information that is emerging from component 3 of this program, so climate model projections. We'll have outputs from component 1, bathymetric and topographic products from LiDAR, and also outputs from component 4, the technical reports of socioeconomic data from fisheries, as well as data sets that countries already have that they would have obtained from LiDAR. One of our aims, ladies and gentlemen, is to improve our ability in the region to just systematically develop and use coastal scenarios. We know the capacity exists. We're looking to expand on those capacities. Finally, then, my colleagues, it's envisioned that the activities such as these undertaken under this consultancy will give us additional information to help our decision makers to plan for climate durability and climate change, and to identify ways to minimize climate-related loss and look for opportunities and ultimately build resilience. Our colleagues, welcome. We look forward to an engaging training event. Thank you so much for joining us. I'll hand back to Simone.
Thank you very much, Dr. Stevenson. And with that, I think we can move into the first presentation, the introductory presentation, which will be delivered by Steve Kemp, at the end of which we would have introduced the rest of the team. And I think I saw that Miguel from OIKO, another partner in this project, joined us. So Miguel, before Steve starts, if you want to introduce yourself. You're muted, sorry. Sorry, Miguel, you are muted.
Good morning.
Thank
yes.
you.
Sorry, thank you. Good morning, everyone. My name is Miguel Trillo. Yes, I'm also a component. I'm part of the team, and I will be also giving some presentations on the last day. I represent OIKO, one of the partners of this partnership, providing the consultancy. I'm very happy to be part of this exercise. So thank you.
Thank you, Miguel. Steve, please, if you could lead us through the introductory part.
Thank you, Simone. Bear with me a second whilst I just adjust that. Okay, good morning, everybody. I'd like to just very briefly introduce the programme of training. Dr. Stevenson has already covered quite a lot of the basics. And say I'm just going to put that into context to set the scene for what's coming over the next 3 days. As Simone said a few minutes ago, you need to have downloaded the software, Invest and QGIS. So I hope you've all done that. If you haven't, then I'm going to take about 15 minutes, and this is the least important of the presentations that you will see and hear. So now's the time to quickly put that right if necessary. The project then is basically about modelling and the use of modelling for looking at coastal change, looking at using models that can basically predict and show us the effects of changes in the coastal zones, using that to inform land use management, land use spatial planning, and putting all that together in the most effective way. The primary focus of the training is on the use of the software, but we will get into application of that as well, with some discussion about different approaches and different possibilities. The 6 participating countries are on the screen at the moment: Dominica, Grenada, Jamaica, St. Lucia, St. Vincent and the Grenadines here this afternoon. This morning we had a session in French for colleagues from Haiti. Dr. Stevenson's already explained the background with the involvement of the University of the West Indies as the driving force behind this programme, and the funding of the Inter-American Development Bank. The overall programme's got these 4 components that you can see on the screen at the moment. This component, this part of the training addresses component 3, which is referred to as downscaling and expanding climate projection models and high resolution mapping. So that is the emphasis of it. And as I say, it's primarily looking at not only how to use how to set up the modelling, how to use the software, but then how to interpret what comes out of that in planning and managing coastal zones. We're providing training then in the use of the modelling tool, and we're going to show how the outputs from that can inform decisions relating to the planning and spatial management of coastal areas. The overall objective then is to help in making decisions to do with planning for the current situation and the situation into the even non-foreseeable future that is going to be dominated by the impacts of climate change and climate variability. Looking at how to identify actions that can minimise losses related to those climate change impacts. Looking also at ways of taking advantage of opportunities that may come from that. And overall, trying to inform the process of building development and places that are more climate resilient. How do we go about this? Well, it's basically by looking at how to develop land cover, land use classification maps and benthic classification maps, focusing on a number of pilot areas where highly vulnerable coastal zones have already been mapped using data that was readily available. Using those, we're going to explore how to use the models to generate a number of scenarios, best case, as is, worst case. So these are alternatives so that you get a range of possible outcomes, possible contexts for managing and planning the future of areas like these. And we're going to look at how to assess and then map socio-economic impacts and benefits based on those different scenarios, so to inform again the overall planning process. The reason for undertaking this training, and I should emphasise this is really an initial round of training. There's only so much you can do in the time available to us, and really this is a starting point. So this will be an iterative process with this laying the foundations. The reason is to enable the stakeholders, the organisations and the individuals involved in the process of assessing change, monitoring change, planning for change, to set up suitable scenarios, to get a feel for that range of possible contexts using the modelling that's available, and to do that by training them to create, edit, update, generally manipulate and use data that's available through these particular models that are readily available and hopefully quite user-friendly once you've been through the initial training. The principal model we're going to be using is the INVEST Coastal Vulnerability Model, which, as you probably know by now, is free and it's an open source software. Important point to note about it is that it produces exposure indices ranked for each point along a coastline. And you can specify the intervals, so you can become finer grain or coarser grain depending on what your requirements are. And the exposure index shows the relative exposure to different factors of the different areas, and I'll explain that in just a minute in a bit more detail. So it's a useful tool in all sorts of ways, not least in assessing the role of ecosystem services and the management and conservation of ecosystem services, and then the application of nature-based solutions to improve resilience. So in a lot of cases that may be looking at ways of restoring damaged ecosystems to put back their protective role. The data that's fed into the model, as I said in that previous slide, looks at a number of factors. So it takes data relating to a number of factors to compute the exposure indices. And those are on the screen at the moment. Relief, natural habitats, wind exposure, wave exposure, sea level change, surge potential, geomorphology. And it looks at those and it ranks them from either very high exposure, or sorry, it depends which way around you go, very low exposure to very high exposure. So it's starting to give you an understanding of the relative vulnerability and risk of different points along a coast. So let me just undo that skip. The workshops, the series of workshops are going to cover these things that are now in front of you. So we're going to be looking at habitat mapping. That's the first element. We're then going to be looking at how to start using the model. Setting out the framework, looking at what sort of data requirements there are for actually making it work, developing the coastal vulnerability scenarios, showing how the model does that, running the model itself to give you some familiarity with that process, and then looking at the different scenarios that are generated. We'll look at the use of the conceptual framework for coastal scenarios, so how you can compare and define different elements of risk and look at that in a spatial way. How to use then the results for land use planning and other types of land use management decision making, which is the ultimate purpose of this. And then looking at further research opportunities and further research needs as the final part of the programme. You've already been introduced to most members of the team. I think from this list, the only member who isn't here this afternoon, I think, is Cassandra, unless she is here.
Yeah.
I'm here.
Oh, you are here. In that case, I think everybody's here. So at that point, I think it's probably best if I now hand over to Jonathan, who is going to be just explaining some of the basics to do with the habitat aspects of this work. Should just emphasise that the terms of reference that we've worked to, coupled with the limitations on travel and time availability, travel mostly because of the COVID situation, mean that we haven't been able to undertake field work to capture new data. One of the things that John's going to explain, because we've had to make use of data that was readily available from some selected pilot areas, John's going to explain how this should happen in the real world, because clearly what you want to know is how to use this moving forward. So this is training, practice, but then you need to have an understanding of what to do with this when you start to use it yourselves. So if I can stop my presentation at that point and hand over to Jonathan, he will take us forward from there. Thank you.
Excellent. Thank you, Steve, and a pleasure to speak to you all. As Steve said, it was a real shame for this consultancy not to have that opportunity to capture baseline data. But as an ICZM specialist, and as most of you on this call have good experience in the types of questions that you've got to pose to decision makers, or if you are an actual decision maker, the sort of information you're going to need, the following 15 minutes is just designed to help to sort of digest the importance of mapping in general, and then to understand that there are certain ways of presenting information and knowledge to help your target audience. And this is where the invest model will really be of use. So the next 15 minutes are just trying to set the scene with regard to why mapping is actually a critical planning tool for decision making in the coastal zone, and also for supporting national adaptation plans around the Caribbean. So as Steve said, you can see in red that one of the key objectives of the consultancy was to work with stakeholders, and particularly to sort of provide the appetite, probably is the best term, to identify what is going to be needed for your individual countries to support your national decision makers in the future. And this may manifest itself in terms of research. It may manifest itself in terms of project proposal writing, but there's a whole suite of avenues that this invest model can provide a service to. So objective 2.4 of this consultancy really is targeted in us presenting to you our findings, our techniques, and how we believe this can really sort of make a massive difference for decision makers in the future. The invest model, as Simone will explain quite soon, really is targeting three key data sets. One is the socioeconomic environment. The second is the physical environment. And thirdly, in red, the environmental attributes. And I'm going to be just focusing on that red area in these next few slides. So, why marine habitat maps? Why are they important? And the key issue here is to acknowledge what is where, why it's there, and of what value does that have to wider ecosystem service delivery. And in order to determine that, there's a suite of issues that need to be addressed and questions that need to be answered. I'll be coming back to these sorts of questions over the next 3 days, but I think it's good for you to sort of digest these and try and determine from your own country's perspective what is actually important. So from your if you are a decision maker, what is the scale of information that is important to you? Do you need that at local level? Do you need that at administrative regional levels? Or do you need it at a national level to dictate policy? Secondly, what coastal information do you consider your decision makers need most knowledge on? Is it to do with flood inundation and erosion, or exposed areas? Is it more about where the communities are and why they're there? Or is it more about why people are congregating in certain areas because of the natural environment that is there? So that dictates your data collection exercise. Thirdly, what level of accuracy do you need? And you'll hear from Simone in the coming presentations and later on about the implications of having different scales and different levels of accuracy of data sets. And we as a consultant team certainly found some of the challenges in getting high accuracy data sets, but that doesn't necessarily mean it is not in your country. So mapping is essentially important. It demonstrates good ways of designing your own surveys that can be representative and can impose consistency with monitoring and evaluation in the future. And that's particularly of value for those countries that I know are present that have ICZM plans in place. Secondly, it shows and demonstrates spatial differential patterns over time. And Simone will explain how the scenario module is very useful in determining that over different spatial scales. And importantly, if you are a decision maker, you need this information as what I'm calling a gateway to identify other sources of information or other potential donors who are interested in this space that you can present some key facts towards. So the map itself is, as we all know, a critical planning tool for decision makers. they assess ecosystem diversity at different scales. They assess the significance of change. You can use them to anticipate the effects of resource utilization or how an ecosystem service is changing over time. They can be used to design cost-efficient surveys and monitoring, and this is valuable for those countries that have set up monitoring and evaluation frameworks to update key national plans on the coast. And finally, it actually helps to identify key priorities that do need budget lines formally establishing to address the issues over time. So what can we use to demonstrate this? Well, the maps show basically where certain habitats are. They can be used as a resource map for overlaying other data sets. The powerful role of GIS is clear to perhaps all of us on this training event. But there are other benefits as well. And a habitat map needs to be embraced in terms of how it can be set up and comprised. And I have a separate set of presentations that I won't give today, but it is how you design your marine habitat mapping program. And for those on the call, we'll be receiving copies of those presentations. But as the habitat map is comprised of different layers and of different details, that means that it opens the door into different users and how they may be able to use the information presented in those maps. So as I've said in those questions that I'd like you to consider, it would be very good in our discussion points later in the training to sort of determine, well, what has worked in your particular country, why it's worked, and what are the missing gaps with regard to, marine habitats, and how you consider how you can use them to demonstrate change or stress of certain habitats over time. Because the determination of those bioindicators of stress really support models such as INVEST that be able to declare and demonstrate change over time. So your decision maker, what does he or she actually need? Well, everyone has different ideas of how a map should look. It would be interesting to sort of get your perspective. How do you see a map looking? What should it show? And how would you use it? Is a map, for example, this St. Lucia example, a series of dots, sort of demonstrating key features on the coast? Or should it be something that contains imagery to sort of demonstrate more of the spatial extent of habitats? Or is it something that has a degree of interpretation? So you're combining those two aspects to appreciate the spatial difference in a certain coastal area of the location of specific habitats. Or is a map a series of spreadsheets? There can equally be as much value for those that have a quantifiable brain to sort of determine how the database feeds in to the output that a map can generate. So there's no real right or wrong answer, but you'll find from the INVEST discussions that there is a need to have a combination of all of these aspects. From a marine habitat perspective, like any model, as you all know the term rubbish in or garbage in, garbage out, it really does rely on as good a quality of data set as you can possibly find. It also needs to be produced by professionals that really understand the workings, the system dynamics of marine habitats. So it's appreciating from the Caribbean perspective an island systems management approach where the ridge to reef model is at the forefront of all decision making. So you need to have an appreciation of the health and the spatial extent of a suite of habitats, for example, as you can see on the screen. But in tandem to that, there's also a need for marine ecologists and marine biologists to provide their input in terms of how biological networks are potentially at play and need to be considered. So that would require a more detailed understanding of substrate type from a physical perspective, different key species, and what are important modifying species that link together the various habitats. So this is all important as you design your marine habitat map. These are the aspects that really need to be available to help support the delivery of a successful INVEST tool. And Simone will explain the sort of success we managed to get down this route. But it's clear from a marine habitat map for those geographers that are on the attendance list that we do need to understand the physical substrate. And so a mapping capability to appreciate different types of substrate are going to be important to determine coastal vulnerabilities in certain areas. So for example, being able to determine muds from coral rubble, carbonate rock platforms or boulders, through to mixed carbonate areas, reef areas, and man-made anthropogenic areas. So the use of LiDAR is critical in being able to sort of determine the footprint of different types of physical components. I won't go into great detail, but from a biological perspective, it's equally as important to determine the range of habitats that will have an influence on coastal vulnerabilities, the service they provide for fish stocks, the service they provide as natural coastal protection, for example. So a lot of the coding that you see here is often linked to international best practice of how marine habitat features are recorded and stored. And this may include different species of seagrass, for example, which all play a different role in fixing sediments and also in terms of influencing current flows particularly in the nearshore zone. There's a need to understand and appreciate different types of algae and the impact that that's having on macroalgae, on the impact that has on reef health. There's a need to monitor and record more detailed information such as sponges, but these particular parameters are not possible to map without doing ground truthing. And that is the issue that could not be fed into the INVEST model that Simone will talk about. But the appreciation of locations from a ground truthing exercise of hard corals and soft corals is an important aspect to embrace. And likewise, the understanding of different types of mangroves. And this is particularly valuable for an ecosystem service issue linked to coastal protection, as well as the support delivery that a blue forest, for example, can provide to local coastal communities. Finally, the types of beach which are present are obviously highly linked to different vulnerable indices. And so the recording of different types of beach will be integral to the success and the scoring that a model such as, and software such as INVEST can offer. So the recording of this information would be linked through to databases, field methods, and like I said, the details of this will be subject to a separate presentation. So linking this all together and being the tee-up person for Simone to talk about INVEST, what is a decision maker going to need, and why are maps so critical, and why can INVEST help to support decision makers for ICZM or coastal adaptation planning? Well, this can be done this is measured in six areas. Firstly, it meets the needs often of local and national level information. And so the mapping process is going to be important not only to support national policy, but there may be international commitments to record against SDG 14, for example, to measure performance of your country against international standards. Secondly, the whole purpose of the map is that it can convey knowledge and it can convey an outreach potential that many words can't do. So it strengthens and it builds capacity on coastal vulnerability issues and environmental management to a range of stakeholders in your country. Thirdly, the map often meets the needs of national biodiversity information and monitoring systems. So your ministries of environment or equivalent, your national biodiversity action plans all probably have a suite of implementation actions on you, which is going to be collecting new and useful data, which is then going to be conveyed in updated maps. Fourthly, some of you I know on the call are in countries that have either set up new ICZM policies and plans or have inherited plans over the last few decades. So the whole purpose of having good maps really is critical to meet the needs of a risk-resilient ICZM process. Importantly, and if it's designed correctly, the setup of marine habitat maps involves local communities in the coastal management decision-making. So this whole purpose of the map is only as good as the message it conveys and also how it can be understood by all viewers of a map. And Simone will explain, and you will see through yourselves through the interactive map production stage, whether you believe that this is the type of technique which is really getting the point across. But if you can actually involve and engage local coastal communities in what it's trying to say, then that really supports the previous blue box, which is meeting the needs of an ICZM process. And finally, and I'm hoping on the call we have good representation from UE and in the postgraduate sort of fraternity, but amongst that, it actually helps to provide education and the appetite for new innovative scientific training on some of the observations that the map is producing. So as Steve said in his talk, we really have an important message to give, and this training will be one iterative process to support that aspect. So the education and the training aspect really, as point 6, is a really important aspect for me to sign off on. So I will pass back to Simone, but like I said, we have separate PowerPoint slides on how you would design habitat mapping programs, which I'm sure can be relayed to you in due course. Simone, over to yourself.
Thank you very much, John. It was really an interesting introduction. Thank you, and thank Steve. So we will now start with the Invest per se program. So let me share my screen. And I will share the all of my screen. So you should be able to see my presentation. Is that the case? Sorry, can you confirm that you're seeing my presentation?
Yeah, all good.
I'm seeing it.
Okay.
Yeah.
Okay. So this first session is about an introduction to the INVEST coastal vulnerability model. In the next today and tomorrow, we go deep into the tool itself, and we'll understand how it works and how you could set up. I will remove these. Yes, we'll remove the subtitles. How you can set it up, create different scenarios, and hopefully utilize it in your day-to-day work and to make decisions. So the content of the training is first a very general introduction to what INVEST is. We will then ensure that all participants have properly installed INVEST, as this is supposed to be, and I hope you will manage to follow through, interactive session, so you can follow me while I'll discuss the different data sets we have prepared, explain it in and open them and explore them within QGIS, and eventually run the model yourself. We will discuss the INVEST cost of vulnerability model in specifically, including the model's conceptual framework, the model's output, the model functioning, and the model's application, including the model's limitation. Now, I'm actually better off, if you're happy with that, presenting in this way, as I will move from the PowerPoint presentation to the QGIS quite a lot. So first of all, I'd like to check with you through a very simple pool. So whether you are all familiar with QGIS, and if some of you is familiar with INVEST, not necessarily INVEST cost of vulnerability model, but others models of INVEST as well. And I just want to check if we have managed to download the softwares, install the softwares, and download the data set. We have prepared a number of data set, which will be the input data. So the INVEST model itself is relatively simple to run, as most of these models are. What takes time is the pre-processing of the different data. Steve, sorry. The different data. We have prepared some of those data input for two of our case studies, for Dominica and Jamaica. We will see that in the next presentation. And we have also prepared a set of data set for Haiti, which we have used this morning for the French training. So first of all, I'd like to get an understanding of how many people have used QGIS, because one of the software we ask you we will use to do this pre-processing is actually QGIS. QGIS is a free and open source GIS software, which means that you can download it for free and you can use it in your project or in your work. It's very similar, for those that are familiar with the Esri family sort of software, is very similar to ArcGIS, which is proprietary on the other end. We have used QGIS because we felt that well, we support free and open source softwares at our firm, and we also believe that it was easier to for you all to download and potentially to use. So if you could please, using the Zoom application, the Zoom raised hand, raise your hand if you have used QGIS in the past. I would be able to get a general understanding of how we're doing, because there's quite a few of us, and if not all of us are familiar with that, I will add here and there some comments on how to use QGIS.
If anybody's struggling to find how to raise your hand, it's under the reactions button at the bottom of the screen.
Okay. So from a quick review, it seems that okay. I have 1, 2, 3, 6, 9, 12, 15 people felt familiar with QGIS, and probably rising. 14 people raised their hands, and we are roughly 70. That's okay. That's no problem. I will, by time to time, put some information on that aspect as well. You could please lower your hand now. And well, I assume that those who have used QGIS in the past have also been able to download it. There is a download link here, and I'll quickly show how where you can download QGIS and what kind of software it is. So you have been sent a link to a page like this, download QGIS for your platform. It works on Windows, it works on Mac, it works on Linux. There is quite a lot of information here on how to download it. We won't cover that part, especially because it takes quite some time for the model to run and to upload. But here is where you can download the actual software. Okay, so we can go back to our presentation. The other aspect that it was sent to you was the case study dataset. So during my training, especially tomorrow, I will load a lot of the second part of today and tomorrow, we will load a lot of this data set. So I like to get, again, a bit of a grasp of how many of you managed to download the data set. So if you could raise your hand if you managed to download the data set, if you have it, if it all worked fine. Okay, so again, we have quite a few people. I'm reading in the chat that some of you is familiar with Esri. The concepts are the same. You could do everything we're going to do in Esri, so there is no problem. Again, I get 15 people who downloaded, and from a quick review, it seems pretty much the same people. So I guess there is a bit of more GIS technical people and a mix of GIS technical people and less people less familiar with the tool. There is no problem. We will manage to work with all of you. Okay, so we can now move to, now that we've sorted that out, we can move to looking at actual InVEST. So what is InVEST? InVEST is a suite of free open source softwares and models that are used to map and value the goods and services from nature, and it's developed under the Nature Capital Project, which is centered at Stanford University, and it's a collaboration between Stanford University and other research organizations and partners. The aim of the project is to develop science-based approaches and tools to promote the integration of the value nature provides to society into all major decisions. So InVEST is not a single model. It's a family of models. There are several different models that we can use. Again, just for your understanding, I will show how the web page of InVEST looks like. So again, you should have been provided with this link from where you can download the whole suite of models for Windows and for Mac. Now, when you download InVEST for Windows, you don't, as I said, you don't solely download one model, you download a number of models, which a sample is here. And the website that I'm showing you has all sorts of information and documentation, which is mostly contained in the InVEST user guide online. So there is quite a well-developed manual that you can use, is sortable online, and it describes all the different models that are there, including a summary and explanation on how to run the model itself. Another interesting tool that is at your disposal when you work with InVEST is the community. So Invest is a free and open source software, as a wide community of people that use it, and a wide community of people that help each other when they encounter problems or when they want to develop the tool further. As you know, an open source software is a software for which you have the source code, which means that you can modify and improve upon the source code and create even new functionalities within the tool itself. So that is quite a number of interesting aspects there. Here is a sample of the models that are available under the Invest suite model. There are habitat quality model, habitat risk assessment model, carbon storage and sequestration models, scenario generation models. Actually, the number 12 scenario generator was part of previous version of Invest, especially the version 3.5. We will be working with a 3.9, but a 3.10 is also available. But it's an interesting tool, and you could download previous version of Invest. They completely work the same, so there's no problem there. You don't always need to have the latest version. We will be focusing on the coastal vulnerability model. So we will focus on that one. We will see what kind of input data is required. We will see how to prepare those input data. And tomorrow we'll see how to interpret results and to tweak those input variables to create different scenarios. In the meantime, I'm just monitoring the chat, and I noticed that someone mentioned that he had problems downloading the data set. So if they could later follow up on that by email, we will try to sort out what's the problem there. Okay, so Invest coastal vulnerability model. What does it do? The Invest coastal vulnerability model uses geophysical and natural habitat characteristic of coastal landscape to qualitatively estimate the exposure to coastal erosion. So when I say qualitatively, is because, as Steve was mentioning earlier, what the Invest coastal vulnerability does and how, the way it should be used is to get understanding, a relative understanding of how much different locations along your coast are more or less prone to or more or less exposed to coastal erosion and coastal inundation due to both climate factors mitigated by the presence of habitats and other physical infrastructures. The model, on top of using the 7 variables that we will look into more depth right now, but and that Steve briefly presented, also considers aspects such as population density. So another thing that the model does, after have calculated the exposure index for different sections of your coast, is that when it is overlaid with data on coastal population density, the models can output can be used to identify where human faces higher risk of damage from storm and waves. So it identifies vulnerability, and that's where the names come from. So it's a vulnerability model because it considers exposure to risk, but it also considers the element at risk, and therefore it can output an estimation of vulnerability. So the model, as any model, is a simplification of certain complex dynamics. As you know, models are not perfect. Models are not meant to simulate every single aspect of reality. They're meant to simplify reality to understand some specific relationship. But as an old saying goes, all models are wrong, but some are useful. and this is a useful model to qualitatively understand this aspect. So the outputs of the model can be used to better understand the relative contribution of the different models variable to coastal exposure, and it helps to highlight the protective service offered by natural habitats to coastal population. In turn, or later on, this information can be used by coastal manager, planners, landowner, and you as other stakeholders, and all other stakeholders to identify region at greater risk and coastal hazard, and therefore enact or act on this particular region through development strategies, permitting, zoning, etc. So this qualitative representation of coastal hazard can be particularly helpful. Now, what is the concept behind it? There are a number of concepts that needs to be considered under that are at the base of the model. So first of all, the model is based on the concept of ecosystem service, and uses an ecosystem service approach. As the invest coastal vulnerability model, as all other invest models, recognize the role of habitats and geomorphological factor play in mitigating the impact of coastal erosion and inundation. So one of the things that the model does when it calculates the exposure index of different parts of the coast, it tries to understand which habitats are nearby, benthic and terrestrial, and how these habitats can decrease the impact of sea surges, coastal waves, local waves, etc. As all other invest tool, the model is a geospatial model. The model is spatially explicit. It maps the relatively exposure in specific location. It uses GIS technologies, and GIS technology has always been often been defined as the science of where, and that's exactly what it does. It provides an information not simply of generally how this ecosystem or physical infrastructure reduces risk, but where does that happen based on the surrounding environments. So based on the spatial distribution of different variables. Therefore, the variables in entry to the model are spatial in nature as well, as we will see shortly. Now, the model is deterministic. It's based on a set of algorithms that do not include probabilities or stochastic relations. So there is no a consideration of chance in the model. This is a technical aspect, but it's important to understand it because it works by rules, which can be understood. But there are stochastic models, there are deterministic models, they are used for different reasons, and this particular one is a deterministic model. Okay, so what does it output? Let's jump the gun and go toward the end of let's place ourselves at the end of this training and ask ourselves, so by the end of this training, what would I get? What would you get is exposure index rank for each points, which are called shore points, along a coastline, which are equally spaced based on a model-specific resolution. So the invest coastal vulnerability model produces an exposure index rank, which is a value from 1 to 5, where 1 is low exposure and 5 is high or very high exposure, for example, in the visualization that you see on the right-hand side, along the coastline. These exposure index are relative exposure of different coastline segments. Although these are points, they actually represent a segment of the coastline which is equal to, on the left-hand side and to the right-hand side of each point, to half the spatial resolution. And these points don't simply have a value from 1 to 5. They have a number of other values that are of relevant, but the synthetic value that you get from all the 7 different variables is this EI, this exposure index rank. And that is what it looked like when you open the attribute table of these points. So the attribute table, for those that doesn't know it, is in GIS a table which is attached to a geographic feature that you load in a geographic information system. So you can load 3 types of data in a geographic information system: points, lines, and polygons. Those are vector data, and we can briefly later on explain what's the difference between a vector and a raster. But what is important to understand here, and we will see it in a second in QGIS, is that each of these points is attached to a number of values which are contained into columns. And this is the value that is attached to point number 1, to point number 2, to point number 3, to point number 4, 5, 6, and so on and so forth. It's an exposure rank. It ranges from 1 to 5, where 5 is very high exposure and 1 is very low exposure. So I think this is a good time to fire up our QGIS and have a look of what does that mean when we look at our areas, just briefly. So this is QGIS. Is not excessively simple interface, I reckon. If you have never used it, do not worry too much about where I click and what I do. I'll try to explain it while we go through it. But as any geographic information system, what it tries to do, or what it does, is to represent data spatially. So you can use it for visualization, and most of you might understand it as a simple graphic tool to create maps, but that's not simply what it does. It's actually more akin in certain uses you can make of it to Excel or to another database, spreadsheet type of software. The only difference with something like Excel is that each of the rows in the tables you have are attached to a geographic information. So there are 2 uses of GIS. One is mostly for, we can summarize it and simplify this in this way. There is one for visualization, graphics, etc., and one which is more oriented toward data analysis, which is the use we will make of it today. So I just want to quickly show what kind of data we would get if we were to load our information. There we are. Let's so let's give it a simple single symbol. Okay. So once we have run the model, what we get in the area of investigation we are interested in is a series of points which are spaced by a distance which is defined by the user. I will make the point bigger to let you better visualize them. So this is one of our case studies, is Dominica. These are the points I was mentioning earlier, our shore points. They are along the coastline. The base map you see on the bottom is OpenStreetMap, is a free base map service. And they're spaced by a distance which you can define, which in this case is 200 meters roughly. So every 200 meters, the model outputs a point. And for each of these points, you have a series of information. With the identify feature, you can click on some of your features and you get some information here. So these are the information that are associated with that particular point, which in turn refer to a particular section of the coastline, 100 meters to the northwest and 100 meters, sorry, to the northwest, yes, and 100 meters to the southeast. And the information we're most interested in right now is the exposure index, which is 2.69. And 2.69 on a scale to 1 to 5 is average compared to the other points. So as I was saying earlier, these values are relative, which we'll see what that means. But the most important aspect is that if you run this model for a different area, you can't really compare the two. You can only compare within the same area using different input values if need be. Another way to visualize this is to open the attribute table. I was mentioning earlier that what a GIS is software, is something similar to spreadsheet software that assigns to each row of your table either a point or a line or a polygon. That's one of the things it does. And this is how that table I was referring to looks like. So you have an ID to identify your short points. The models create actually two. We will see that later, but they're basically the same value, but -1. Some software start counting from 0 and then go on. We will see what rank habitat is, what rank wind is, what rank wave is, and what rank surge is, and rank relief and rank geomorphology are. We will see what population is later on, but let's focus on exposure for now. So exposure is the 1 to 5 value I was mentioning before. So point number 70 has an exposure index of 4. If you zoom on that, you can do with zoom up to the selected row, remembering that each row is connected to a specific point, reducing that, we get one of our point. Now, you may notice that that point is separate from the coastline. That's probably because of a difference between how OSM has mapped the coastline and the actual coastline we have utilized. That may happen, but depend on the land mass input data that you provide. But I hope that I have given the understanding that each of these points is given a value, and each of these points is actually representing a section of the coastline. The fact that each of these points is representing a section of the coastline means that they would be nicer if they were presented as lines rather than points. And to improve visualization, that's something you can actually do. You can transform those points into lines to get a more precise connection with the coastline itself. You also notice that in these slides, the one that I'm showing you right now, and these other two, the points are color coded based on that exposure index. That is something we will see how to do tomorrow, because as I said earlier, one of the benefits of QGIS is that you can use it to visualize information in a relatively nice and clear way. And so we will try to use it for that purpose as well. Okay. Right. So, invest coastal vulnerability model. How does it work? The model computes the coastal exposure index by combining the rank of 7 biological and physical variables. It considers relief, it considers presence of natural habitat, so the natural habitat distribution, both biotic and abiotic, and both benthic and terrestrial. It considers wind exposure, and it considers wave exposure. We will explain how those are calculated briefly. It considers surge potential and geomorphology as well. So the geomorphology is, although is an optional input variable, is quite an interesting one. It's based on the idea that rocky cliffs are less prone to erosion and inundation than beaches or deltas, but also that seawalls and embankment and groins, etc., so man-made structure, are less prone to erosion. So the geomorphology input here, although optional, is recommended for inclusion, and it should represent the different man-made structure, gray infrastructure that are there as well. The sea level change, again, is optional. We will see later on why we have not used it in the way the model uses it, but how we have incorporated, or we can incorporate it, notwithstanding. Just so I did a very quick review of this. Let's dig a bit more in depth. So relief is elevation above mean sea level. It's based on the fact that sites that are on average at greater elevation are at lower risk of being inundated, so than areas that are lower elevation. So definitely, if we do create a conceptual model of how erosion and inundation works, relief must be one of the aspects we consider. Natural habitat, it relates to what we said. It relates to what we said earlier in terms of the fact that marshes, seagrass beds, mangrove, coastal dune play a vital role in decreasing the impact of coastal hazard, and that can erode shorelines in armed coastal communities. So the coral reef breaks large waves. Mangrove and coastal forests dramatically reduce wave heights, decrease the strength of wave and wind generated currents. Seagrass beds and marshes stabilize the sediments, encourage accretion of nearshore beds, and etc. Wind exposure and wave exposure. So strong winds generate high surges and or powerful wave if they blow over an area of sufficient period of time. So the wind exposure is an output that rank shoreline segments based on their relative exposure to strong winds, while the wave exposure ranks areas on the relative exposure to oceanic wave and wind generated local wind generated waves. Surge potential is another important aspect. So storm surge elevation is a function of wind speed and direction, but also the amount of time the wind blows over relatively shallow areas. So the models uses a series of inputs to generate that surge potential. It estimates the relative exposure to storm surges by computing the distance between the shore points and the edge of the continental shelf. Again, we will see where to get the continental shelf data, and the model manages the rest. So basically, if we go and have a look at how these different aspects are considered, we understand that the conceptual framework for the model is to use, as we said, geomorphology, so morphology of the coast, including man-made structure, natural habitats, relief, climate dynamics, so wind, wave, and surge potential, as well as sea level rise, to compute a single value. So out of 7 values, he summarizes it, he synthesizes it into a single value for each shoreline points. And he does that by calculating the geometric means. So the multiplication of a value 1 to 5 assigned to each of these elements, and then taking to the power of 1/7. So you can understand how this value, being the combination of all values that can range from 1 to 5, it actually will range to 1 to 5, because if all these values are 1, this will be 1 to the power of 7. So 1 times 1 times 1 times 1 times 1 times 1 times 1 to the power of 1/7. So that would be 1. If it's 5, it will be 5 to the power of 7, because it's 5 times 5 times 5 times 5 times 5 times 5 times 5 to the power of 1/7. Now, if you use only some of these input values, it will reduce there. So if you only use 6, it will be to the power of 1/6. If you use only 5, it will be to the power of 1/5. Now, geomorphology then. How does the model assigns values to these different aspects? Some of them are based on percentile distribution, and some of them are based on categorization. The categorization element is it has a component of user definition. So when the models needs to quantify for example, the geomorphology, it gets in input a geomorphology vector file that tells him where it's rocky, where it's seawall, where it's medium cliff, where it's bulkhead, etc., etc. Each of these typology are assigned with a value 1 to 5, and the model takes an average of the different geomorphology typology that it finds around each point. When it comes to the natural habitat, the calculation is a bit more complex. The model still looks around each point to find different habitats. For each different habitat, it searches to a different extent. And when he found some of these habitats, each of them is associated with a protection level 1 to 5, and it uses an algorithm which it's a formula to calculate this number, which again is it's a rank which is squeezed in a 1 to 5 distribution. The other are relatively more simple. They are percentile distribution. So for each point, first the model calculates an absolute value. Then it compares that absolute value with all the other absolute value for all the other points that he has identified along the coast. And then he bins it into different percentile. And for the first percentile, 0 to 20, it gives a value of 5. For the second percentile, 21 to 40 percentile, it gives a value of 4. So these are actually quintiles, basically. It does that for relief, and it calculates relief by ingesting a dam, looking around each point, averaging the different heights it identifies, and inputting and getting that absolute value. It does that for sea level change. So it looks around each shore points and search for information on sea level change, which are provided by specific input data set, and calculate that. It does that for wave exposure as well as for wind exposure. The wind and wave exposure are a bit more technical. We won't go into details of the calculation, but I can give you a very quick look at the manual, the user guide, which you find again from we will send all these links, but you can find it on the Invest User Guide, and then you can navigate to the cost of vulnerability model. You get all information here, including the way. So here we have our model, our calculation for the exposure index, which you can more generally write in this way, in a more mathematically formal way. But you get for each type of input variable, how that has been calculated with the proper formula and the proper references to the different aspects. So for wind exposure, it calculates the relative exposure index. And for wave exposure, it calculates a mix of power from coastal waves and from wind generated waves. And again, it's important to understand, what's important to understand here is the difference between those variables from which the rank is calculated based on a categorization. So assigning different categories of values and then calculating some values. And those that instead are calculated as an absolute number and then being using the quintile distribution. Okay. So I mentioned earlier that the manual refers to a lot of different scientific articles and bibliography. I just want to mention, I didn't mention it at the beginning, there is quite a lot of literature on the use of Invest Coastal Vulnerability Model in the Caribbean as well as elsewhere. So there's quite an interesting study done in the Bahamas, which was one of the sources of inspiration for this project, which we could have a look at. They have an interesting web app as well, which if we have a second, we could probably have a look at. There it is. So this is the results of a different project, but it uses Invest, and what it does, it calculates our hazard index from lowest to highest. They define it as a hazard index, but the proper name is exposure index for the Bahamas. We can have our imagery here, and you get all sorts of information, including natural habitat. You should be able to see it, probably just if you move to terrain. There it is. It's loading slowly, but you could see the natural habitat appearing, so such as seagrass, coral, mangrove, etc. And we will see in our case studies rather than this one how these habitats provide some protection. But this is just an example of the different literature that you can find on this topic, and most importantly on the use of Invest Coastal Vulnerability Model. So, okay, we have seen our different input variables, our 7 different input variables. The last aspect that interests us is for this presentation, for this first presentation at least, is the population density raster. So we mentioned earlier that all the information that the model uses, there's a typo here, sorry, allow me to fix it. Okay. We saw earlier that all the input variables that the model uses are actually done to calculate an exposure index. But exposure is not vulnerability. To have vulnerability, you have someone or something that is vulnerable to whatever they are exposed to. And this can be calculated using the population density raster input to the model. So by providing a density information where population are located, And this is done through a raster. And here comes the difference that I was mentioning earlier, that may not be that familiar for people who are not knowledgeable about GIS, between vector data and raster data. So vector data are those points, lines, and polygons. But if you have a continuous value, so values that change throughout the space continuously, such as density. Density range from 0 in certain areas, that increases in urban areas, that decreases again, but it's continuous across the space. You need to represent that with a raster. A raster, it can be simplified as a grid, where each pixel has a value. And for density, population density raster, that value for each grid is how many people live in that particular square. But you can have raster for other type of information, geographic information. We will see that when we look at land cover and Benthic cover. So ideally, you could have, or you could imagine having this massive grid where each pixel is color coded or given a value based on the type of land cover, Benthic cover that is actually there. And the step of your grid, so how big each of the squares needs to be, it's the resolution of your raster. So if you have a raster such as the one I've described for population density, you can feed it to the model. And what the model does is calculates the number of the people, the density per square kilometers around that particular point. Why is that useful? It is useful because you can then filter and query for those points which are high exposure and very dense. Because points that have high exposure value but have no one living around it are not particularly interesting for a decision maker. On the other hand, points that are of low value, low exposure index, low exposure value, so they're relatively sheltered, but they're surrounded by high density population, have a lower priority compared to those points that have both high exposure index and a lot of people living nearby them. So it helps you identify areas where you need to intervene, you need to plan, you need to zone, you need to put measures in place to manage that risk and reduce that vulnerability. This idea of querying the data you have, it's crucial when you work with GIS, with Geographic Information System. That's exactly what the models allows you, what these tools allows you to do. They're not simply to show a map, they're actually to inquiry data within a map. Now, we just started to talk about what we could do with this model, and we could go and have a look at other potential application. We will focus on different application in the last day of the training. But here I want to give you a bit of an understanding of what the potential useful useful outputs of using something like inverse cost of vulnerability model are. So the first one we just described, identification of vulnerable communities. You could identify vulnerable communities in the way I've described earlier. What also you could do, if you have the input data set, is that if you imagine having a raster, so a density distribution of your population, but not the whole of your population, vulnerable member of your population, you can refine your analysis even further. So if instead of having number of people per square kilometer, so number of people in each of the pixels in the grid that was our raster, we had number of elderly people, number of households living below poverty rate, we would refine our vulnerability analysis, and it would help us identify even better vulnerable communities. Obviously, provided that we have that sort of data. Overlay and proximity analysis. You can imagine that, let's open our QGIS again, just quickly. Okay, so we mentioned earlier, we have our points, and we could start looking at how many people live around each of these points, trying to identify the points with the highest exposure index. I will actually do that. So I will color code these points based on that exposure value. We will see in more detail how you do that, but in QGIS, you could pretty much change the symbology and color coding of each feature class based on those attributes you have in that table I showed earlier. So you could graduate based on one of these attributes. Remember, each of these points have a value for exposure. There it is. So you could tell it, make exposure lighter when it's low and darker when it's high. And we could do that either through equal count or different way of breaking down your data sets. But equal count with 5 classes for us will work. We could even use when it's 1 or when it's between when it's below 2, so which is between 0 and 2 excluded. So basically when it's 1 or around 1, make it white, and when it's around 2, make it pink, and so on and so forth. But this distribution will probably work well for us. We have a number of points here which are dark, which means that their value is high. And as I said earlier, we could calculate how many people live nearby there. But we could also do something else. If we knew, for example, where schools are, we could start querying the GIS and say, tell me where each school, which is within 2 kilometers, 1 kilometer from one of the red points is. And you can identify a specific school, which is likely to be a risk, because this tract of coast for our model, it's exposed. That is what we call an overlay and proximity analysis. Estimation of ecosystem services. That's another interesting aspect. So we will see that in the next session. But what the model does is, as we saw, use the presence of habitats to calculate that exposure index. Now, what would happen if habitats was not there at all? The model automatically calculates the value as if the rank index, the rank habitat, so as if, there we are, as if this value, this number here, was 5 for each point. So instead of being 1 because that particular shore point is protected by a mangrove, or being 2 because it's nearby a mangrove, but there are parts of sands in front of it, etc., it's always 5, which is the highest exposure it can have. By doing that, for each point, the model calculates an exposure index with no habitats. And then by this, the subtraction between exposure in the without habitats and exposure in the with habitats, it calculates an habitat role. So again, we will do that. We will see how to do that. You could color code or query, these points either based on their exposure no habitat, and we reclassify. We should probably, yeah, we could reclassify, or we could color code them based on the habitat role. And here, let's use a different color range. Let's use a range of blues, where dark blue means that the habitat role is high, and white means that the habitat role is low. So here, these areas are somehow protected by some habitat, which is in front of it or nearby it. We noticed earlier that their rank was, the exposure index, even with habitat, was quite high anyhow, but it would be worse without those habitats present. And by calculating that, you get a qualitative, not a quantitative, but a qualitative understanding of the role of ecosystem services. And with further analysis, you could even assign or make some estimation and monetize the reduction in exposure index would have in terms of damages and in terms of damage avoid assessment or avoidance of damages, and so on and so forth. Other ways to utilize the tool are infrastructure assessment. Infrastructure assessment, we mentioned earlier that the geomorphology input variable is optional, but it's recommended for inclusion, and it plays a role. It plays a role because it represents the presence of man-made structure. So although this is a model that is meant to be used to calculate ecosystem services, you could also use it to run a scenario where a seawall is there and a scenario where the seawall is not there. And you see how that exposure index change. And you get, again, a qualitative understanding of how important that particular infrastructure could be. So here we are in the region of scenarios already. There would be one of the different scenarios you could run with this model, with this tool. Another interesting scenario, which we have touched upon, is the idea of changing the land and benthic cover change analysis. So earlier on, we said, okay, let's run it. The model automatically outputs an exposure index without width and without habitat. But when it does it without habitats, it removes all habitats. So what if we want to run it with just either specific section of a particular habitat removed to represent, for example, mangrove loss of mangroves, death of certain section of coral reef, or if we want to run it with the whole coral reef removed to showcase the importance of the habitat, or if we want to run it with an actual potential likely cover change as a result of climate change and as a result of man-made, anthropogenic, other sort of development related pressures. You could also work with the climate change in terms of climate change analysis. If you modify the wind, wave, and sea level rise variable, there's a typo here, this should be the other way around, we will correct that. But if you modify the wind, wave, and sea level rise variable, you can run different scenarios in terms of climate information, climate variables. Now, this is a 3 days training with 2 days on the model itself. It's a lot of information, and I already understand that you might be tired. We will do a break in 2 minutes. But what I want to say is that we won't cover all the different potential scenarios or potential typology of scenario you can run. We will try to keep things relatively simple, get you a basic understanding of how the model works, what kind of input data does it need, and how you can run very simple scenarios, specifically with benthic cover change. That will be tomorrow. We will run a scenario with benthic cover change. We will briefly touch upon how you can create climate change, different climate change scenarios. And from there, we hope you will have a base to implement your use of INVEST and move forward in that direction. Okay, so we have talked a bit about the the advantages of the model. So we can close this first session with a bit of the limitation. So first of all, as I mentioned earlier, it's a model. It's a simplification of dynamic interaction in complex coastal processes. And it does not consider coastal processes that are unique to a specific region. It works in the same way for Jamaica as it does for Poname in Micronesia. By the way, the images you saw here in different of the slide that I presented are from the Poname Island, Micronesia, and the maps were prepared with a sample data set available on Invest. We'll see later on where these sample data are, because as I briefly discussed, Invest is quite good in providing support, in providing training. The guideline is quite well done, and when you download the software, you also download a number of data sets that you can use to follow their own trainings. So the model does not consider any complex interaction between the different. Hello?
Yeah, I think you're back on. You're back on. Good.
Sorry, there was some issue with, I'm not sure if my connection or.
You're back on, so it doesn't matter.
Okay, right. So share that part. So it simplifies connections. That's necessary to an extent for a model such as this that deals with such complex relations, etc. It does not value directly any ecosystem service. It ranks sites which are relatively low, moderate, or high risk of erosion and inundation. They're not absolute values. They cannot be compared across countries, but only within the areas of investigation. So although I show you some case studies from Dominica, you have a data set for both Dominica and Jamaica, and we will see how to run both of those. But they shouldn't be compared. You can compare within scenarios if you run it on the same AOI, area of investigation, but not across different regions. Okay, so these are the key limitation, and I think that concludes the first theoretical part about the Invest model. I suggest we have maybe 10 minutes break, and then we walk into the last session. Unless there is any burning question, we can take a couple, I think, before we break. If you could raise your hand if you have a question. Okay. I
think Robert has got a question.
Okay, go ahead, please.
Thank you for a very interesting overview of the model. I was just wondering if, well, really the extent to which the model will allow you to play a bit with the parameters. So for example, if I didn't want to use percentiles, for example, for, say, one of the parameters, I wanted to use absolute values, I'm just, throwing something out there. Does it allow that type of, manipulation or customization?
Okay. Yes, it does. Well, the model per se doesn't. The model per se, unless you're able to enter the code and modify the code itself, it does not. you can, and we will do that with sea level rise, force its hand toward the end. And basically, we will provide the different inputs. But the problem of using absolute values is that they won't be comparable across them. Returning everything to a 1 to 5 rank, although simplistic in a sense, allows to compare the value the contribution habitat has with the contribution of geomorphology has. Because otherwise, if there were some absolute values, for example, for wind and wave, if it was wind in meters per second and wave in energy, in watt or kilowatt, those values, those numbers won't be comparable unless you bin it somehow to a similar scale. So you have that normalization problem.
Mhm. Okay, thank you. Thank you very much.
Any other question before we break? We'll ask my colleagues and people from UE to monitor the. Okay, right. Yes, in that case, we can have 10 minutes break and meet here at 11. Would that be okay? Okay, perfect. In that case, I'll turn down my screen for 10 minutes. Let's have a quick break and then look at the different input variables and actually running the model.
Great, thanks, Tony.
The sweet potato has over 700 varieties worldwide and 120 in the Caribbean. In Jamaica, we can find 30 varieties, with 4 being drought tolerant. The ganja, white-fleshed, has shown to produce a high yield. The yellow belly, which is also white-fleshed. The Clarendon, another white-fleshed variety, and the Uplifter, the only yellow-fleshed drought-tolerant potato of the 4.
So let's make some breakfast with them. This is a simple yet filling breakfast hash. Sweet potatoes are high in beta-carotene vitamins, antioxidants, and fiber, a great way to start the day.
Peel and slice the potatoes into bite-sized cubes. Then, partially cook them in some salted water. After about 5 minutes, they should be tender on the outside. Drain and set aside to cool. Next, we saute some bacon.
You want to saute the bacon until it's half cooked before adding the onions and peppers.
Then spice it up with some red pepper flakes and paprika. Remove the bacon and in the same pot, crisp up the potatoes. Make sure to crisp on all sides. So now we add in the sauteed bacon with the potatoes.
Sweet potatoes are a healthy alternative to processed carbohydrates. Garnish this with some scallions and serve with your favorite eggs. Now, this takes us to lunch. Sweet potato is a complex carbohydrate and is perfect for making a delicious filling soup. Before you begin, gather and prepare all your ingredients. Start by cooking the curry powder and leaves, chilies, and masala.
After about a minute, add the onions and garlic and cook until soft.
This is a great way to use a mix of the potato varieties in one dish. Potatoes grow relatively quickly and have a good shelf life. Once the potatoes are coated in the seasoning, you can add water and stock cubes or a salted vegetable stock. Bring to a boil until the potatoes are cooked and falling apart. Then it's time to blend until smooth and creamy. Time to serve and garnish. You can even keep it completely vegan and add coconut cream instead of dairy cream.
Hello, welcome back. Thank you for the video during the break. That was quite interesting, and
I'm going to be spending the rest of the day in the kitchen now. So
yeah, definitely tastier than my presentation. Okay, so I will restart with the second part of this presentation. The actual running of Invest and the input variables. Now, if you have not installed Invest, I will show you how to launch it. If you have installed Invest, you can try to follow through and open it yourself as well. So let's go and have a look at the model, the actual Invest software, because so far all we have seen was QGIS software, which has, reminder, we only use to pre-process and post-process the data. It doesn't do the Invest component of it. The Invest software does it. Note that Invest is not a plugin to QGIS. If you're familiar with QGIS, you know that QGIS is extension. So it has different bits and parts that do specific things, which are developed by the users. Invest is not a plugin. It's a separate software. So we can save and close this one. Sorry for that. Okay, so to run Invest, all you need to do is you search for it in your file locator, and what you should be able to see is deep within your programming, you should find the Invest 3.9 x64 software. So what do you have here are all the models we were seeing earlier from Invest. I encourage you to have a look around in Invest itself. As I mentioned earlier, some of these are quite interesting stuff. It's all free, and there is quite a lot of information. Just for your understanding, I will now show you what kind of sample data you can get for each and every one of these. So if you navigate to, sorry, it's in for me where I save it, but that's the default location when you save Invest. You go to see program files. Well, that's Invest 3.10, but should work anyhow. You get the documentation, including the user guide. Sorry, that's not where I think it's located. Okay, I'll show you later on because I'm not able at the moment to pull it out. But if we go back to our list of models, you have the different models here. So the models we're interested in is the coastal vulnerability model. If you double click it, it would launch it. So the way it does that is start with, don't be scared by the window behind it. You can actually reduce it and ignore it. And this is actually all Invest is. So it's just a GUI, a graphic user interface, where you want to point the model to where your data are. So let's clear it for a second. This is already a setting of different data sets, the one that you could download as well. The model is quite intelligent. It remembers from the last time you run it where those pointings are. So it can retrieve those data if you want to run the model again. But you can either save this configuration and load it again. So it will just automatically load. I need to look for these here. I need to look for this there. I need to look for these here, and so on and so forth. Or you can just clear it. So it will slowly clear all the different aspects. What I just want to make you understand, this is pretty much Invest. All it is, it's this interface. It needs some parameters which are input by you, and we will see how and why you input certain numbers rather than others. There is next to each input variable, there is a folder locator, so you can go and look of the different data that you want to load, or you can drag it there, and we can do that as well. And then you hit run once you have loaded all the different files that you are supposed to load. So that's pretty much it. So what is the difficult part? The difficult part, obviously, is to prepare the different data, understand the type of model you want to run, the type of scenario you want to run, and set the parameters to represent the type of the complex model, the complex solution you want to model. So that's pretty much the most complex part. Now, some of the data that we are seeing here, let's minimize it and have it here just for our understanding. We will see each and every one of these, but just as a reminder, some of them are raster data. So that continuous surface, that grid-like type of data that I mentioned earlier. Some of them are vector data, either as points, lines, or polygons. And some of them are tables, while some are actual values that you enter, they're parameters. Now, raster data, for those familiar with GIS type of data, raster data can be either as they can only be TIFF.TIFF. So you want to be sure that your raster data is saved as a GeoTIFF file. Point vector data can be pretty much everything. They can be shape files, they can be GeoPackage, they can be GeoJSON. I'm not gonna dwell on the difference between all these different aspects. You may be most familiar with shapefile, and you may actually use shapefile as a term for all sorts of vector data. But there are actually other formats. Shapefile is simply a format for vector data. It's an Esri proprietary format, but it's became so widely known that everybody uses it. It has these advantages because, as it may have happened to you, shapefiles actually, there's only one of the different files with the same name, which is a .shp. All the others are files that the .shp needs to work. And if you load it without those, you don't see anything in QGIS, but they need to go together with it. So you have the 7 files that all have the same name, different extensions. They need to travel together. It's a bit of a pain sometimes. So you can instead use GeoPackage. And although the models takes in input shapefile, GeoPackage, and GeoJSON, it does outputs a GeoPackage, which is a better way to manage things. Tables needs to go in as comma separated values, CSV. So they're simple, the simplest way you can structure a table, and you can open it in any spreadsheet reader. You can use LibreOffice, you can use Excel, you can even use QGIS itself. You can open a table in QGIS. That's one of the power of the tool. So, okay, without further ado, let's start looking from the very start what the models require. The first one is the workspace. So the workspace is nothing else than a folder where it will save all your outputs. You can simply create it by clicking on the folder here. If you leave your mouse there, it should tell you what that does, but no, okay. So if you click on it, it will tell you, okay, where do I need to save this? Where is the repository? Where is the folder where I need to place all these things? And you could put it on your desktop and give it a name. You can create a new folder and give it a name. Naming conventions. Generally, when you work in QGIS as is anything else, you don't want spaces and you don't want capitals letter. You want everything lowercase. You don't want because it's easier for the computer to manage. In this particular case, you could call it out, standing for output, underscore. We will work on Jamaica just because most of you, at least from the attendance sheet, were from Jamaica, so you may be more familiar with the case study area. So we will work on Jamaica, and we can call it scenario 1, say, and we can put a date. We can put a date which would be interesting for us. So that would be 01/02/2022. So we know that it's from today. So you select the folder and he knows that he needs to save everything there. You can give results as suffix. So because you can run several scenarios within the same folder. It has advantages because it will be quicker if you do that. So if you only change one variable, as we mentioned earlier, all the different variables are calculated separately, and then they're brought to synthesis when it comes to calculating the exposure index. But that means that if you change the variables that affect a specific rank, say the variables that affect the habitat ranks, but you don't change all the other variables, it doesn't need to recalculate those. It already has that. So if you run it within the same workspace, it should do that. That is what the user guide says. In my experience, that sometimes leads to problem because it doesn't always work. So my recommendation, although it takes longer, it's all the time, create a new workspace, give it a proper speaking suffix, and that makes it easier. The suffix is what it adds at the end of each scenario to the name, to the file name, so you can recognize and understand what that particular run was. So we can call it underscore result 1, for example. Okay, now it asks for an area of interest. Before going to work on the area of interest, let's have a look a second of our case study areas. So I mentioned earlier that the French training was using case studies from Haiti and the Jamaica, and then the English one the data set we provided you, we use a case study from Jamaica and from Dominica. The case study from Haiti is from the Jeremy Kayamai area. The Jamaica one, which we will be using, okay, we can remove this part. I will explain you what that is. The Jamaica one is an area that runs from Kingston to Moran Bay. The maps you see here have a Benthic cover class. They come from a report that we prepared when we had to select the case studies for this training. And we had actually 3 options in Haiti, and 3 options in Jamaica. And we developed 3 options for Dominica as well. For Dominica, the case studies is from the Northwest Coast, from Point Reposoir to Point Michel. Now, I was saying we had different options for each of these countries. The options for Haiti and for Jamaica were influenced by the component 1 of the PPCR project. So the component 1, improving geospatial data management and management for adaptation planning, included data collection done by the LiDAR data collection done by Fugro in 3 locations in Haiti and 3 locations in Jamaica, which was the options that we had. That provided us with the DEM, the digital elevation model, and the bathymetric model. We will see in a second why those information are important, both to calculate one of the 7 variables, relief, but also to calculate the wave and surge potential. So getting DEM and bathymetric data, especially bathymetric data, was crucial and was difficult. If you run this model yourself, you will find out that 2 of the most difficult data for you to collect are exactly this one. There's especially when it comes to bathymetry, there is very limited free and open source data at a resolution that you can actually use for something like this. So the work done by Fugro was pivotal, was really helpful. Helpful for us when it came to first decide where in Jamaica and Haiti we would focus, and later on, among these 3 locations in Haiti and 3 locations in Jamaica, select the one we would use for our case studies. Data completeness of data in those areas was an important factor for us. There were other factors that we considered in the selection of our sites, and we ended up selecting. So we consider other aspects such as exposure to natural element, presence of ecosystem, which this map is one of the visualization of, importance of community, and social vulnerability of the site. And these analysis led to conclude that these 2 case studies for Jamaica, again, sorry, there's a typo there, for Jamaica and for Haiti were the most appropriate. When it came to Dominica, we had a different source of bathymetric data and digital elevation data. It was a project called Light Detection, Ranging LiDAR, Bathymetry and Topography Survey, Data Analysis, Modeling and Development of High Accuracy Terrain and Bathymetric Models, which was developed in collaboration by the Disaster Vulnerability Reduction Project. Yeah, there's a typo in the map. Sorry, I probably have loaded a previous version of the map. It's been corrected in the reports. So that was developed by as part of the Disaster Vulnerability Reduction Project, supported by the World Bank, and it was done by Mac Elani Consulting Limited from Vancouver, Canada. They were very nice in providing the DEM and the bathymetric data for this project. It covers the whole of Dominica. We had different options as well, and we used the same criteria to select this particular area. So that is basically, if we go and have a look at our area of interest. Actually, let's jump to our area of interest section. That is our first requirements. We need to provide an area of interest. We need to tell where do we want to run this. It should be a polygon feature class. It should be larger than the coastline we want to analyze. If you know what that means, it means it should be projected coordinate reference system, and this should be in meter. That is a bit of a technical aspect, but when we talk about projected coordinate, it means that it's basically, since the Earth is round, you could represent things in degrees and on a round surface, but what we want here is in meter flat. and that is how you get projected data. You can manually define it, but it's better to buffer, either to buffer the 0 meter contour line, or that you can extract from the dam, so you actually get the proper coastline, because you have the dam, you have negative values. Remember that the dam is a raster, so it's a continuous representation of information. And some of the pixels you have are negative because they are below sea level, some are positive because they are above sea level, and some are 0, and that's your coastline. So if you extract that line and then you buffer it, you get a really nice area of investigation. This is what has been done, is shown on this map here. So we got the coastline, and then we buffered 2 kilometers each side, and you get a relatively interesting area of investigation. You could actually draw it if you want, it's just not as precise and as relevant. So you shouldn't have too small of an area of investigation, not too large of an area of investigation. That being said, that's not exactly a rule. I've seen published paper done for a very small section of the US, a delta of a river, as well as for the whole west coast of the US. So it ranges from a very different way of utilizing it. So let's go and have a look at our area of investigation. So we are in Jamaica. We are roughly where we want our location to be. We have set our coordinate reference system to meters and to coordinate reference system that is appropriate for Jamaica. I won't explain that in any further detail, but that's one of the requirements of the data sets we provide. And we can go and open the actual folder that we have sent you. So the folder that we have sent you, that I hope you managed to download. If you haven't, try, and if there is still a problem, let us know. Has 2 different folders. The one we're going to look at is the Jamaican one. So there is a Dominica one and Jamaica one. They're exactly the same in terms of tree. So folder tree, folder structure, but the data inside are obviously different. We want to look at the input. We'll see the miscellaneous later, but let's look at the input and its structure with all the different input that the models requires. The first ones we want to look at is the areas of investigation. Now, these look like different data sets, but as I mentioned earlier, they're shapefiles. So they actually refer to a single one, but they need to go all together. If you miss one of these, you probably won't be able to open the shapefile itself. So QGIS is quite intuitive. If you take this and you drag it almost anywhere within the tool, it will load. Okay. It will load, and you need to drag it to the very top to be able to see it. So it needs to be the first things you see. And that is our area of investigation. We took the coastline, we buffer it, couple of kilometers. Could have done more, we could have done less, 2 kilometers. It was the areas we were interested in, and that's the file we want. Now let's start populating our invest as well. So it wants the areas of investigation there. And again, since it's quite intuitive, let me close some of other folders that are not relevant and keep open only the one we want. You can simply drag it. So you can take the shapefile and you drag it there. There, it's green, it got it, it's happy. Excellent. Now, the next thing it requires is the model resolution. The model resolution is a parameter. I can't load anything there. I need to type something. What do I type? I type the distance in meter between the different shore points. You may be tempted to input a very small number to get a lot of information. Now, you should be considering two aspects. First, high resolution means high number of short points, which means a high computation time. So it's slower. The computation time is actually slower because it takes a lot of time for him to calculate every information he needs to calculate for each point, then move to the next and to the next and to the next and to the next and so on and so forth. And most importantly, depending on the resolution of the other data input that you have, you may not get additional information by having a very high resolution. So a very low resolution, sorry, a very high resolution, a very low number. So you probably want to test the model with the different resolution, potentially starting with an high one, see how long does it take to compute and then lower it. For Jamaica, for this training, we recommend using 400 meters. It might seem a lot, but we don't want the model to take forever to run. Even with my computer, which is quite powerful, it takes 15 minutes to run, so it could take some time. But that model resolution, it depends on the type of information you want to explore and to the scale you're planning or managing for. You plan at a certain scale. You do a national spatial plan, you do a regional plan, you do a local plan, you change the scale. And according to when you change the scale, you need to change the way you look at things, the resolution you look at things. Now, I'll try to move a bit quicker through this presentation because I'm aware of time, and there could be, I don't want to run too long, although we may need some time taken from tomorrow's presentation. That wouldn't be a problem. The landmass. Now, the landmass, what is the landmass? The models needs the landmass, know which parts, which areas are above sea level, because it wants to calculate exposure. So what it actually does is for each point, it looks in different direction and see how far it can look in a particular direction before encountering land. So for example, let's go and look in our GIS. Let's turn off the area of investigation for a second. Let's imagine we are here and there is a short point there. It will look in different direction and see if it finds land. If it finds land, for example, when it looks straight to the west from this point, it would find the tip of the Port Royal Peninsula. So it knows that from that direction, that particular point is sheltered by land. If there was an island here, all those points would be sheltered. And that is important for the model to understand where there is open sea and when there is actual sheltering land. It doesn't look everywhere. It looks in 16 directions. So it looks north, northwest, northwest, northwest-west, west, and so on and so forth. Sorry, the other side. So it looks in 16 specific direction, and it does that creating what it calls rays. So it traces these 16 rays in these different directions until it finds land mass. It also uses the land mass to place the points, because it knows that the land mass it's where is 0 meter above sea level. So let's try to load our landmass. We have prepared a landmass shapefile. You can drag it there. Again, you want to put it to the top, and there it is. This is a landmass for the whole of Jamaica. Now, you don't need the whole of Jamaica, because we are only looking at a particular area within Jamaica. Sorry. You want a landmass that is bigger than your area of investigation, because there could be islands outside of it, and it traces, it looks along this race, it looks for quite a distance, but you don't want the whole world. So you don't need the South American coast in this case, because it won't look that far. It will stop earlier. But you want a relatively extent landmass. Where do you get the landmass? You have really two options. You can derive it from the 0 meter contour line from your dam. So you have your dam, you extract the 0 meter contour line we mentioned earlier, and you transform that in a polygon. That in QGIS, we're not gonna do it, but it's relatively simple to do. Or you can download OSM data. The map you see on the background is OpenStreetMap. And when I open this file, you should see that it follows it very neatly. It does that because what I've done, I have downloaded it from OpenStreetMap. OpenStreetMap is free and open source. You can download pretty much everything from OpenStreetMap and use it. So it's a good source of data, not solely for the use in a project like Invest, but for all sorts of different projects. So we have defined our landmass and we can load it. So it looks for a landmass, it needs a vector, it tells you which type of data it needs. There is even an information box next to each thing, and it tells that it needs a path to a polygon vector representing land masses in the region of interest. So there it is. That's the actual path to that particular shape file. Okay. So excellent. See if there is anything else that I need to mention about landmass. No, that's pretty much it. Okay. So we're starting to populate our cost of vulnerability element. What else do we need? Waywatch tree. Now, I might ask Teddy to jump in here a second to help us understand what this Waywatch tree dataset is. But I'll show you first. So Waywatch tree is a point feature class. So it's a series of points which is provided by Invest. So it comes with the Invest tool. And it's based on wind and wave data compiled from 8 years of NOAA Waywatch tree model. And it is a global extent. So it covers the whole of the globe. When we go and load it, so if you go back to our folder, we have it here. We have a subfolder called 03 Waywatch tree Jamaica. Here it is. Now we have global and local. I'll explain in a second why that is, but let's load the normal one, the global one, which is the one that it's provided by Invest itself. So if you zoom out, you'll see that it covers the whole world. It covers the whole world. It put up a point every roughly every 5 kilometers, and each of these points have a series of information. Yeah, go on.
I think it's longer than 5 kilometers. So the Waywatch 3 is about a 1/4 degree resolution.
Right.
Yeah. Which is approximately 25 to 35 kilometers or so, depending on your location.
Okay. Yeah, thank you, Teddy.
But I think you're looking at, are you looking at the local or the global data set? Because it might be different.
No, the local data set.
Okay.
I will explain now. So the local data set is just basically a cutout version of this. I can load it. Here. So we have loaded it. Let's put the local on top. So look what happens when I turn off. So you can turn off and on layers. When I turn off the global data set, some points disappear because we have just collected the local ones. This is done solely for a presentation purpose and for a training purpose, because running there are two things that make the model run very, very slow: a very high resolution, and the other things that it needs a lot of time to calculate is the wind and wave exposure. So with a lower number of points, the model is a bit quicker, and that it's useful for us now because we don't have a lot of time to make the model run. But normally, remember that when you run it, you should run with the global one rather than the local one. We will run it with the local one for presentation purpose, but you should run it with the global one. But that being said, what kind of information are in here? Maybe Teddy could help us understanding that a bit better. And I don't want to go into many detail, but what basically the information there are a very long set of number, which are the ray in all different directions. I mentioned 16 directions. There they are. V0 is 0 degree direction. V22 is 22.5 degree direction, which is 22.5 degrees to the west. And then V45 is 45 degree direction. It's wind coming from that direction, calculated at that point. It's wave energy calculated at that point from that particular direction. It's the percentage of wind coming from that direction and the percentage of wave coming from that direction, and so on and so forth.
Where the sum of all the percentages add to 1. So it's the relative contribution of the wind coming from that angle relative to all the other angles. Again, exactly. It's really just extra information, a lot of background, but it is interesting to see how much detail can be extracted from here if you're really interested in seeing the details inside the engine.
Yeah, absolutely. And so for most of you, it's just the data set that you load and run. Or for those of you that are interested in modifying climate variables, this is the data set you modify, because this is the data set the models uses to calculate wind exposure and wave exposure. Okay, so let's run quickly through that, and let's just add it to our model. It needs, sorry, I lost. All right, Jamaica, perfect. So he needs to know where the Waywatch 3 dataset is. Where do you find this data? We have provided it to you, but you also find it in the sample data from Invest. We said that you normally would need to give it the global one. This time we're going to give it the local one, but just for understanding. Now, it now needs a parameter, maximum fetch distance. What's the maximum fetch distance? We mentioned earlier that it looks around each point in different directions until it finds land, or until it reaches a certain maximum. That maximum is the maximum fetch distance. It's a numeric value. It's used. It's necessary for him to get several types of information. So when he looks, when the model looks along the array for the wave, for the surge potential, it looks for depth, water depth. So it needs below the benthic cover, sorry, the DEM, the digital elevation model, and it looks for depth of water along the array. It looks if it finds a landmass. It needs it for all sorts of different things. 30 kilometer, between 12 and 30 kilometers is an accurate value for the scale you're probably going to be look at. So we recommend 30 kilometers is what is recommended in the documentation as well of the model. So it's something that, again, you can't simply input it. You just need to type it. You punch it in. It's in meter, so it needs 30,000 meter. but it's you just need to understand what does that means. It's basically the distance that it looks around. And it looks around each 16 directions. Now we see here in their image, just a few. We just see 3 and 3, 6, 8 of those. But he actually looks in the others. They're not shown here because he immediately finds land. So it doesn't cast those rays, but otherwise it would. The other rays you see here are all the other rays casted by each other point because he repeats the process for each point.
Simone, may I make one quick comment that might be helpful? Definitely. So the reason that we're talking about the fetch, or it's the distance over which the wind blows, is the wave height is limited in 3 things: the duration of the wind that's blowing, the wind speed, but also the distance across the water that the wind blows. So that's why we're looking at the fetch distance, and that distance is called fetch, because the longer of the distance it blows, the greater your wave exposure will be.
Thank you. Thank you, Teddy. Yeah, it's exactly why the models look at that, and thankfully we had Teddy on board with us, because I'm not a meteorologist, I'm not an expert on wave and wind, but we could use his expertise on these particular aspects of the model. Okay, so how are we doing? We have given it the maximum fetch distance. It seems to like it. It put it green, that's fine. What does it want? Bathymetry. Path to our raster representing bathymetry. Bathymetry values should be negative and units of meters. Positive values will be ignored. Now you have 2 options here. You either have a bathymetry raster and a digital elevation raster, where the bathymetry is negative and it doesn't have positive values, you only have zeros, and the digital elevation model is positive and doesn't have negative values, or you have a single dam with both values inside, which is what we have. It is what we have, and it lies in our folder. So let's jump up a second, jump up again. We're back in our list of inputs, and we have dam. Now, this is the actual dam, the teeth. These, and anytime you see a .qml, that's a symbology. It just tells GIS how to color things. And this is how you should color it. So what are we looking at? There is a legend here that you can see on the side. Let's make it slightly bigger and more evident. Okay, so this dam, if you zoom deep enough, you will notice that it's actually made of squares, and each square has a value. Minus 29.30, minus 32.52. When you look at a distance high enough, it looks like it's continuous, but it actually is not. It's that grid we were mentioning earlier. That's what a raster is. So you can start to discern the different parts. So you have something that is 0 or very low above the sea level, 1.45 meter. We have things that are very low, minus 0.4, and so on and so forth. You can have a look at the actual resolution. If you basically, this is the measure line. So the measure line now puts information here. Let's clear it for a second. New line. So how big is this square? That's 25 meters. So each of these square is 25 by 25 and is assigned a single value. Obviously, there's a lot happening in those 25 by 25 meters. It's not flat with one value. It's just a way to simplify, because otherwise the data set will be too big. Okay, so this is our dam. This is our positive and negative dam. So we will use it both for our bathymetry and for our digital elevation model. Where do we got this dam, and where can you find one for your own regions. We got this dam thanks to the work done under component 1. I mentioned it earlier. LiDAR data collection has been performed for this area, as well for other areas in Jamaica by Fugro, and LiDAR data has been then transformed into a digital elevation model at a resolution that was much higher than the one we just saw. We were actually provided a 5-meter resolution, which is quite impressive, but probably even too much for our model. It would make it run, it would make it very heavy to run. So we resampled it to 25 meter. Now, not everybody is lucky enough to have a LiDAR collected for your area of interest, and there is where I said that is the most difficult component of dataset to retrieve. You can find them on different repository online. The USG, there it is. The USG Science for Changing World is one of the many websites where you can download them. They're not most of the time at the resolution you want or you need. So unless your areas of interest is quite big and you're happy with 50 meters resolution, you won't find much in terms of terrestrial dam. And it's even worse when it comes to digital, to bathymetry. So you can get JEBCO dataset. Some of them are free, some are not. But again, it's very difficult to. So here is JEBCO, General Bathymetry Chart of the Oceans. Most of these data are you need to pay for it. Only a few of them are free. We couldn't find free data for some of the areas we were interested in. So as you may remember, St. Lucia, St. Vincent, and Grenada are also part of the PPCR project. We did look for bathymetric data on that. We requested them. We didn't manage to get it. So, and we couldn't look at all of each and every country for our case studies. So we decided to focus on Jamaica and use the LiDAR data. But if you do have the data, if you do manage to retrieve it, if your government has it, you're good to go. And what you want to do is to load the digital elevation model. We mentioned that it's a single raster. So what the model does for the when it comes to the digital elevation model, it only considers everything that is positive. When it needs bathymetry, it considers everything that is negative. It does it automatically. You don't need to do anything else except put the dam here and put also the dam in the same thing, bathymetry. It discerns the two things by itself. Okay, so we mentioned earlier why it needs that. It needs that for two things, for two reasons. First one, it needs to understand the relief. Higher points are less prone to erosion and inundation. So it considers that when it calculates the exposure index, but also it needs to know the depth to calculate into the ocean wave factors. So it needs to cast the array and see how deep is the sea bottom along the lines it looks at. Now, when it looks at the elevation, it does it around each point, and it looks for a certain distance, and then it averages the digital, the data, the elevation data it gets. There it is. So between 500 and 1000 meters is considered adequate. 500 meters is most of the time fine. It depends on your points, points resolution. It tends to be close to your points resolution, slightly higher than that, so you can cover more points. So we will use 500 meters here. So around each point, you will look 500 meters and collect data it needs for that. Okay, so the bathymetry and digital elevation are used for the relief exposure rank. The dam should be an adequate scale, so not too coarse, such as 50 meters, and not too detailed, just like 50 centimeter. 5 meter to 25 meter resolution is sufficient. The other data that it needs is a continental shelf contour. But the continental shelf contour is used to calculate storm surge potential. So in general, the longer the distance between the coastline and the edge of the continental shelf at a given area during a storm, the higher the storm surge. And the model estimates relative exposure to storm surge by computing the distance to the shore point. A data set of continental shelf, it's available as part of the sample data set. It can also be retrieved at the link here, Ephraim Comage, Continental Data Margin. So when you load it in, and again, you can load it in the same way, it's a vector file, it's a line file. So you go up from your aspect, continental shelf, and you chuck it in. It's there, and if you zoom out, you notice that it's global. It's a global data set. Now, a point for the more experienced of you. Vector data needs to be all in the same coordinate reference system, with the exception of the continental shelf and the Waywatch 3 data. They're global data set. They can be in WGS 84, but the others data set, vector data set, needs to be in a specific coordinate reference system, the one that it should stay the same. This is an example of, this is considered a bit of an approximation of storm surges. I've seen academic papers that finds other solutions, so they override the way the models calculates that. To go back to the question that was asked previously, so you can do these kind of things. You can tell the model, okay, I'm going to ignore the rank, the coastal, for example, the continental surge rank you calculate, and I'll give you a different one, but it still needs to be in a 1 to 5 binning. You can just find a different way to calculate it. Okay, so let's load the continental shelf. Now, we're running a bit out of time. So what I am prone to do is we load the last few data set without, if you have followed me, you should have been in this position. You should have loaded either the data set for Jamaica or the same thing, but for Dominica. So you would have put it things from a different set of folders, but from Dominica. So if you followed me so far, we are in this situation. We will just look at the last, we will load the last 3 data sets, but we will explore them tomorrow. What I just want to do is to be sure that we hit run by 12 today, sorry, by 5 p.m. today, because the model takes some time to run. I'd like to let you leave your computer there for a bit to run it, so it start chunking things. So let's just load the last few data set we need. It needs a geomorphology data set, so we put it there. And it needs a geomorphology field value. Okay, let's explain that real quick. And then tomorrow we just need to explain the habitat table and the population, human population, which are big elements. Geomorphology. Right. Here is the geomorphology data set. It's a line data set. It's a polyline, which is a line feature class, presenting the geomorphology of different sections of the coast. So what it does is basically you have different lines. Let's make it a big thicker, so we can have a good look at it. Better. Okay, so you have different lines. Let's look here. That let's have a look here. That follows your contour. If you turn on your landmass, sorry, if you turn on, I don't have it here, but if you turn on your 0 meter contour line, it would follow that exactly. It should follow that. Yeah, it should follow that pretty neatly. What are these data? So each of those sections, each of those lines is assigned with a typology and with a rank. There is beach, there is high cliff, there is seawall, and there is a number attached to it. What is that number? The number is the relative exposure index of that particular type of geomorphology coastline. It's low when that type provides protection, when the exposure is low, and it's high when that type does not provide protection. Seawalls is 1 because they provide a lot of protection. Normal beaches are 5 because they're very exposed. High cliff, medium cliff, etc. plays a role as well. Medium cliff is value of 2, high cliff has a value of 1, and so on and so forth. So here is the geomorphology part, is where we are talking about man-made intervention. So for example, here, when we look at the Palisados Road, if we go and have a look at what is this, is marked as seawall and is given a rank of 1, because whoever digitized this, which is one of our colleagues, identified a seawall there. Now, a word of caution of using the dataset we provided. We digitized it solely for presentation only. So we did it using we did it based on satellite images, and it might not be extremely accurate because we didn't ground truth it. We didn't go on site and check if it was the way it was. So it's there, and you can see it's optional, just to show you what that type of data set is and how you could modify it if you want to improve accuracy, and more importantly, simulate the presence or absence of certain man-made structure. What's the geomorphology field value? You don't need to have that geomorphology following the whole line of the coast you have. You can only have bits. If you only have a data set which shows seawalls and you don't have the location of beaches, that's fine. You run it with seawalls and you tell the models, if you don't find anything, put a specific value. It needs one value that is 1 to 5. And in this, most cases, 3, it's an average value because you don't know what's there. It could be another seawall, it could be a revetment, or it could be a beach. A beach would be 5, a delta would be 5, a revetment, a groin would be 1 or 2. And that's the way you run the geomorphology part. Now, with the aim of hitting run by the end of this session, what we're going to do is we will load the habitat table, which is here, there, and I will explain tomorrow what that is. And we will load the population raster. And again, I will explain tomorrow what that is. So I'm always in these folders. You find all the different data sets. They're all organized and numbered based on the number of input you need to put. You have this raster data. We'll look at it tomorrow. It needs a population search radius. We give it 1 kilometer for now. I'll explain tomorrow why. And we'll skip the sea level rise for now. It's optional. We can skip it. So once you have this configuration, you can hit run. You're ready to run the model. You have parameterized the model as you wanted, and you can run it. When you run, it starts to do what it does. So it provides you information. These are useful to, in case you find an error. In the community that I showed earlier, whenever you have a problem, they will ask you to upload this bit, because they're very proficient. They can read these and understand what kind of problem you're encountering, if you're encountering one. So that kind of information is quite helpful. Okay, so we will cover the rest of this presentation and the next presentation tomorrow. But I think we could spend 10 extra minutes for some question, if there is any, while this runs. And if you followed me, which I hope you managed to do, you should be seeing the same thing in the model thinking. So sorry for running a bit long, and thank you for your attention. If you have any question, any comments, we could address it today, or if it's something that we will explain tomorrow, look at it tomorrow together.
Quick question.
Yeah.
For the last one, the population search radius, what was the amount in meters again?
1,000, 1 kilometer, 1,000 meters.
Okay, thank you.
Okay. We're seeing comments here. Where I think having the data viable is very important. Yes, data viability with most models you run is an issue. The models is quite nice because it works with mostly it works mostly with it can work with some proxy data, but as I said, one of the barriers that we have experienced is the bathymetry data. The bathymetry data is probably one of the most difficult to obtain. That's why LiDAR component is so important. Yes, recordings will be shared to like the review of and practice tonight. Yes, I think Erica, is there any way to share the recording today?
Yes, as soon as it has converted, I can share the link with the registered attendees.
Okay, thank you.
Please ensure that you have completed the registration attendance register for today, so that I can share the recording with you. I will resend the link in the chat just now.
Okay. I got some comments that some of the text is too small and that I'm probably running too fast. I apologize for that. Tomorrow I'll be sure to zoom in more on some parts, and I'll try to move slower. Again, apologies for that. There was a lot to cover in one session, but maybe tomorrow we'll have a bit more time to go through some of the previous parts. Yes, the model, the data set should be a RAR. If you download it, it should be a zipped file. Has anybody been able to open the zip file? Can someone confirm me that you have been able to open it? There are some people that are not able. Yes, okay. Program like Itzark to open it, give some data. I could try to resend it as a without zipping it. Okay, so first of all, I'll try to send it. I'll send a fresh link to download the data set. And Erica, if you could help me circulate it without the zip, if that helps extracting it, some of you. Other aspect that was mentioned is that someone is having issues opening the Invest software. I will circulate some further documentation on how to download the tool. Okay, I think that's it for today, unless there are any other question, any comment. Okay, it might be normal that it takes a bit of time to open it the first time. That happened to me the first time as well. So let me know if it does open eventually. Okay, great, excellent. Okay, so thank you all, thank you everyone, and hopefully tomorrow we will have our result done and we can look at it together.
Okay, well, thank you, Simone. Thank you, Teddy and John, also for your contributions, and thank you everybody for paying attention and following what I think has been a very interesting presentation. Hopefully, we'll get opportunities to get a bit of a conversation going tomorrow, but we have to get a lot of information across in this session. So, thanks very much, and we will see you tomorrow.
Thank you.
Thank you, everybody.
Okay.